Yes, welcome. So today we talk about geometric sequences and geometric series. Unfortunately, I have to turn the music down a bit. So here I give you a geometric sequence. Bn is a times r to the n, r is a positive number. And these arise already as very simple models for populations. So let me show you how this works. If we assume that Bn is the population number at a time unit n, and now the time unit can be days or it can be hours if you look for bacteria, for example, or it can be months or weeks if you look for larger animals. So n is a time unit, Bn is the number of the population at that time, and r is the number of offspring they produce per unit of time. Then the population size on the next day, say, is r times the population size on the previous day. And then we give an initial condition which says how many animals we had at the beginning of the experiment or beginning of the observation. Now we can find a closed formula for this recursion, right? This is a first order recursion, but we can sub it in, so we can write this to be rbn. But now for bn we can use the same recursion, so then this is r times rbn minus 1. And then we can use the same recursion again, and we replace bn minus 1 by r times bn minus 2. So maybe step by step. So this is r squared bn minus 1, then this will be r to the power of 3 bn minus 2, etc., etc. And then this goes to r to the n plus 1 times b0. b0 is the initial condition, so this is r to the n plus 1 times a. So we have already an explicit solution for the bn plus 1 for this simple population model. Now, it doesn't matter if you write it in n plus 1 or in n, so then I can also write this as bn is a times r to the n, and indeed, I have my geometric sequence right here as a population model. Let's look at typical graphs for the population model. So here I show three graphs. One is increasing, one is stable at 1, and one is decreasing. And this has to do with the rate of reproduction r. So if the rate is bigger than 1, if each individual produces more than one offspring per unit of time, then the population grows. And the limit, as n goes to infinity, of r to the n is infinity. So this is the curve for r bigger than 1. If r is equal 1, then r to the n is always equal to 1. So then this is the curve for r is equal to 1. And if r is actually less than 1, this means on average we have less reproduction from day to day. So then we have 0 is less than r less than 1, which is the decaying curve. So geometric series also arise in a more complicated model, which is a model for drug delivery. So let's look at this. So let's say Cn is the drug concentration at day n in a patient in milligram per milliliter of blood. And I assume that 70% of the drug is consumed or washed out during a single day, which means 30% of the drug remains from one day to the next. And 0.2 milligram is added daily to make up for what is lost through the body metabolism. So the question is, write down a mathematical model for the drug concentration in the blood, and what is the asymptotic blood concentration in the body of the patient. So as a model, we use a recursive model. So we write down the blood concentration at the next day, Cn plus 1, is 30% of the previous blood concentration. So we have 0.3 times Cn, but then we add something per day. So then we add 0.2 milligram per day, and very quickly we have our mathematical model. So this here is from previous day, and this is added daily. So it makes a lot of sense. Now let's see how this looks like if we graph this on a computer. So here I show you a view graph. I start with 0 concentration of drug on day 0, but then I have the model which we just derived. And here I show the view graph, and you see it is increasing from 0 after the first delivery, the second delivery, the third delivery, but it does not continue to increase. It kind of settles to a constant level. It settles to a constant level. And of course, the doctor would like to know what is the level, what is the constant level of drug exposure in the body. because this is the target. This is what a doctor would like to know. So we will show you now in this video how to compute this number, how to compute the asymptotic level of the drug in the blood. For this, however, we need to talk a little bit about geometric series. The geometric series is the sum of the geometric sequence. So here I call it Sn, and this is A plus AR plus AR square plus and so on plus AR to the n. This is a formula which we will need just in a second for the drug delivery problem. Now, wouldn't it be nice if we have a closed formula for this Sn? And indeed we do. So we can show that Sn equals A times 1 minus r to the n plus 1 divided by 1 minus r. You can see this is quite a complicated formula, and you can easily imagine that the derivation of this formula is a bit hard. So I diverted to another video which you can watch if you are interested. For now we take this formula in the box and we use it in a second for the drug delivery problem. Try at some point to remember it. It might be very useful. And the drug delivery problem had this form, right? We had Cn plus 1 is 0.3 times Cn plus 0.2. So it has a form of a linear recursion. And here I write down a general form for a linear recursion. So Bn plus 1 is r times Bn plus c. So B0 is the initial condition. B1 then is r times B0 plus c, so which is Ra plus c. Easy. So B2. This is RB1 plus c, which then replacing B1 with Ra plus c, and then multiplying this out, then we get this is r square a. And here we get an RC term and a C term, and I can write this as 1 plus R times C. So the next term, B3, is RB2 plus C. So we sub all this in. Then we get R times R square A plus 1 plus RC. Multiplying this out, we have an R to the power of 3 times A. Okay. And, oh, I forgot my plus c here, I'm sorry. And then we get a term rc, we get an r square c, and we get a c. So putting this all together is 1 plus r square c. If this is too quick, then please take a piece of paper and follow it through on the paper, and you will see that this is correct. So now if we go on and on and on, then we get r to the na plus 1 plus r square plus etc. plus r to the n minus 1 times c. And now we see a wonderful thing. So this here is a geometric series. Geometric series, right? It is r to the power of n, and we add it up to the number n minus 1. This is great. So we can use the formula for geometric series, which means we get Bn as r to the na plus, and now we use the geometric series formula with an exponent n minus 1, so then we get 1 minus r to the n divided by 1 minus r, and all this times c. So then this here, I'm sorry I'm a little bit running out of space, but this here is the solution for a linear recursion. We have an explicit solution formula now. And then of course, now we would like to apply this to our drug delivery model from up here. Okay. So here's the drug delivery model again. And so let's write down the solution. So the A term from before, this was a 0, so we start with 0 drug concentration on the first day. So what we really get is then C times 1 minus r to the n divided by 1 minus r. C is 0.2, 1 minus 0.3 to the n divided by 1 minus 0.3. So, and 1 minus 0.3 is 0.7, which we can then put up front. So we got 0.2 divided by 0.7, 1 minus 0.3 to the n. And then this is the same as 2/7 times 1 minus 0.3 to the n. So we get a wonderful formula for the drug concentration, and this is in fact what describes the curve. This is the same curve as I shown before. In the limit as n goes to infinity, then we have the limit as n goes to infinity of 2 divided by 7, 1 minus 0.3 to the n. So we use our limit laws, and this is the same as the limit as n goes to infinity of 2/7 minus 2/7 of limit as n goes to infinity of 0.3 to the n. Now the first term has no n in it, so limit of 2/7 is just 2/7. And the second term has a limit of 0.3 to the n, which goes to 0. So the result is 2/7. So this value here is 2/7. Now we got it, and we used the geometric series, the formula of the geometric series, to compute this. So let me summarize. A geometric sequence has a form Bn equals a times r to the n. A geometric series is the sum of all those first terms. So a plus ar plus dot dot dots plus ar to the n. An explicit formula for Sn we found to be a 1 minus r to the n plus 1 divided by 1 minus r. A linear recursion is a recursion of the form Bn plus 1 is r Bn plus c. And we found an explicit solution for a linear recursion to be Bn is c times 1 minus r to the n divided by 1 minus r plus r to the n a. Oh, yeah. Hi, Gerlo. Hey, what are you up to? What? You're building a geometric sequence? That's actually funny. Well done.